Good day. My name is Michael Tong. I'm going to be discussing the quantum computing applications, and I'm from Heriot-Watt University. This is basically the layout of what we're going to be covering, and it's going to be going on like this. We're first going to start off with the introduction and why we're going to be discussing quantum computing applications on a IMechE speaking out for engineering kind of a talk. And next we're going to go into current uses and how does it work. And afterwards, I'm just going to go into my own speculations. Now, why are these developments important to us, right? Well, I remember that a lecturer once said to me that, we as engineers, all we do is basically help society run smoothly. And, there comes to a point where you have to optimize the amount of tasks that are being done rather than optimizing the tools we use to actually do those tasks. So time that would otherwise be wasted, right? That could be used to help develop a business or help help you spend time with your family or just help you pursue your passion or have more time to relax. Another reason would be reducing our carbon footprints. So like greedy corporations, right? They won't. I don't think they'll be changing their ways anytime soon. And with the rate of climate change, if we don't make any drastic changes, right, to anything, we're just going to be heading downwards towards extinction. The first thing I want to discuss is car paint shops. So normally what happens, right, is that they incur a lot of costs and waste due to them swapping colors when they deal with all the customers at once, right? So what quantum computing has allowed us to do, right, is that it's allowed us to basically cut down the wastage to 20%, and that allows the manufacturer to actually paint 5 times more cars per color swap. Next, we have Save On Foods, which is a grocery store, right, based in Canada, and they normally spend 25 hours per week on an optimization task. You can imagine like managing logistics and such, or managing like supervisors. But what quantum computing has allowed us to do, right, is to cut down that time to 2 minutes, basically. Next, we have train platforming and managing passenger flow. So what it actually does, right, it just generates the most optimal path for you to take, and it allows for optimization of timetables and maintenance schedules. Moving on to routes optimization, right? So waste collection vehicles, they normally employ diesel engines, right? And we all know here in Malaysia that they're quite they're very bad. A lot of smog comes out of those machines, and what quantum computing has allowed us to do, right, is to cut down the number of vehicles by 59% and actually reduce the CO2 emissions by 57. The last thing I want to touch on when it comes to applications is actually traffic routing. So actually what we actually have developed now, I suppose, not too long ago by Volkswagen, is that they've developed the first quantum optimized bus. And what I mean by that is that I'm not sure why I'm showing you this. You probably can't see my notes. But I took notes during their webinar at about 2 a.m. And what they actually said was that using the traffic data provided to them, they used the GPS data to optimize their routes with the QPU by considering each car as a qubit. And normally with conventional computers, you would actually have the response time being a few hours, and you can't have that when you're dealing with vehicles, right? So it was reduced to about 120 seconds, and actually it's had no failure. So there's 100% reliable shuttle service. Now, why are quantum computers so good, right? So what they're specialized for, right, is actually having small inputs, small outputs, but having for those situations a large array of possibilities that could happen in between that small time frame. Next, I'll be discussing basically the main principles that we use, as well as how we still use classical computers to control these quantum computers. I'm going to go over the differences between bits and qubits. So classical computers, they use ones and zeros to actually represent the state of transistors. So they're either on or off, and that's binary, right? It can either be 1 or 0. But for quantum computers, they use devices that can be manipulated, so have their quantum state changed. So they can either be spun up to represent a 1 or spun down to represent a 0, or they can be spun, in between using superposition. And why that's important is that that's what allows them to actually store a lot more data and do a lot more calculations at the same time. that simultaneous up and down. Starting off with superposition. Superposition is basically the idea that like these quantum particles can be in multiple states at once, which is very unintuitive. I made a little diagram here to illustrate a Schrödinger's cat, and Schrödinger's cat is a very famous thought experiment to basically outline how paradoxical the concept was. That and basically what it was is that you have a cat, a flask of poison, as well as a radioactive material. They're all stuffed into a sealed box, and the idea is that right, the cat is both alive and dead at the same time once it's inside the box, because you can't observe it. Once you observe it, it will collapse, kind of like the wave functions that they have in quantum physics, and that will collapse into what we know as alive or dead. The next concept I have for you is entanglement. So entanglement basically is that when two objects are so close together that they can only be considered a two-object wave function. So this is a very difficult thing to describe because these two particles then can be separated to the other ends of the universe, right? If they're not disentangled, they will still be what's called linked mathematically. Now, I've come up with an analogy I haven't seen anywhere yet, but hopefully it makes sense. I'm just going to go a bit closer. So, you need another person in the room to do this. So, have them close their eye, right? And start with one eye open. Just look in any direction. And, the idea, right, is that even though you cannot see where this one is facing, you instinctively know that it's facing the same way because, that's just how human eyes work. So, there. But basically the concept, right, is that if you have one of the particles that's entangled, you can actually measure how the other one will be spun exactly. The last thing I have for you is interference. Now, interference, as we know it, it can be constructive or destructive. So whether you want to add on to the wave's amplitude or if you want to, I suppose, cancel it out. So something we use in everyday life for some people is noise cancelling headphones. And noise cancelling headphones, they use the destructive interference to actually utilize the microphones that are on the outside of these headphones to actually cancel out the sound waves that are being projected onto it. So you perceive it as like you'll have no sound coming from the outside. That's the idea of it. But how we use this kind of feature in quantum physics is that they will amplify the correct answers by having constructive interference and destroying the wrong answers by using destructive interference. Okay, what it actually is that it's used to control quantum states and amplify the type of signals that are closer to the correct answers. And lastly, I'm just going to go over, what are qubits and how do we actually control them with classical computers. So qubits are basically just devices that have manipulatable quantum state. Some examples are atoms, ions, and superconductive qubits, which is the most advanced version that's being used by Google and IBM. We use our classical computers to actually send microwaves through cables to chips with qubits on them. And what these waves actually do, right? These waves just, if you send a certain frequency as well as a duration, you can control whether the qubit will go into superposition or it'll become a 1 or a 0. And if you send a microwave through two qubits at the same time, they will be entangled. So that's how you achieve that effect. Lastly, I want to go over how I speculate that they could be used in the future. Now, something I'm really looking forward to is actually simulation. We use simulation in engineering now. What are simulations, right? So simulations are dynamic representations of models. So what we use these simulations for is that we use them for many different reasons. We're going to go over in ones. The first we have is military systems. So we have things like missile, air defenses, as well as undersea warfare. We then have something more defensive, such as homeland security. So we can cover things such as disease spread, traffic evacuation, that sort of thing. And even for medicine, we have a use for it, right? We have a surgery simulation. Because, many things can happen during a surgery. And you want your surgeon to be ready for that when you're saving an important person or anyone in general. What aspects are there in a simulation, right? So first we have resolution. So like how many pixels are on their screen for us. But in terms of a simulation, it is actually regarding the degree of precision and detail of the real life variables inside your simulation. Second, we have a fidelity. So basically it's kind of going back to how accurate it is to real life. Lastly, I want to go over aggregation. So what that really means is how well your system can actually group entities and maintain the behaviors that they exhibit while inside those groups. So you can imagine, right, when you're choosing a player for your football team, let's say you want to add someone else, and somehow you're able to get Messi, right, one of the arguably best players in the world. So with the level of which quantum computers can operate, they can actually more or less predict how players would interact with one another. So let's say you're the manager, you're selecting Messi. But if Messi, right, if Messi doesn't play well with your team or their playstyle simply doesn't match, right, you could be wasting millions of dollars by selecting him. And if I'm allowed to quote a article here, it says here that we ran a simulation experiment that shows that aggregation seriously worsens estimation accuracy, and that the impact increases with the order of aggregation, right? So how many things are linked. But what I'm really interested in is actually a quantum simulation, because of what it actually does, right? Instead of taking I suppose, a large number of summations or using maths as a way to kind of model the universe, it can actually just model the universe itself or the environment you want to replicate, instead of going another way around it and making a lot of adjustments along the way. Now I'll be going over our limitations and where we're at in terms of the developmental cycle. Okay, so the number of qubits we need to actually perform calculations that are useful and reliable enough that classical computers cannot compete at all is actually 1 million. The quality of the qubits and such matters, but generally that's the number we gravitate towards. And currently the maximum we have is 50, so we're a long ways away from actually reaching the goal. And why scaling up these qubits are so difficult, right? It's because they're very sensitive. You know, their greatest asset is also their Achilles heel. Is that they have to be kept at near 0 Kelvin. They can't interact with any light or any radioactive waves. And there's such a thing as quantum vibrations that can affect them. So I'm not even sure what that is, but it sounds very difficult to manage. But I have a lot of faith in this field and how much it can develop. Hopefully in my lifetime, I'll be able to observe that how this quantum computing will actually develop. And one aspect I was especially interested in is actually how we're going to interact with it, maybe as a programmer. So when I attended this webinar that was intended for, I suppose, manufacturers that was looking towards using quantum computers, right, is that there is a decent amount of manufacturers that actually look into the matter and planning to using it in the next 3 years or so, according to D-Wave. So take that info with a grain of salt. But even now, we're able to interact with some of the quantum computers via, I suppose, D-Wave systems. So you can access them through online sources. And when I was given the opportunity to ask them whether we'd have QPU programmers or something like that, or coders who were specifically geared towards programming these quantum computers, the answer they gave that it will always be a build versus buy argument for each business.
But our last question is from Michael. And do you see a possibility where companies would hire programmers for QPU specific coding, for example, using Leap?
So what I might say there is that I think every company is going to for itself have to consider a build versus buy kind of a decision to make. In some cases, it's going to make sense to build up your own capability in-house, like what Volkswagen has done with their data lab. In some cases, it's going to make sense to actually contract out and hire some resources. So I think it's very realistic. The nice thing is that in fact, those programming skills with the technology stack that's available now and the Python programming that's open source, it's actually not a big leap. For many people, it's actually a very close conceptual leap to what they're already working with.
Right. So Volkswagen, they have one person in-house. In the whole IT team, they have one person that's dedicated to making applications.
Which is kind of like an internal IT consulting group within the VW organization. Our role is to identify emerging technologies and do applied research to help the VW group grow. My role specifically on that team is to work solely on quantum computing applications. My background is in physics and computer science. I've been at VW for almost 3 years now, and I've been working full-time on quantum computing for just about 7 years, starting with benchmarking, research and development, and now I focus solely on building quantum applications. So I'm going to...
And where they're looking towards developing is actually, over here it says machine learning and simulation, kind of like what I mentioned. But these are more futuristic plans, so we're not sure when it's going to be developed, maybe a few decades time even. But I think it's very promising. And for youngsters to get involved, I think it would be it's a very exciting field to get into. Thank you for listening.